Now we're going to be talking about energy in waves. We know that waves clearly carry energy. We only have to think about earthquakes and storms at sea. And clearly, our intuition tells us that big waves carry more energy than smaller waves. We see this when we have a large-scale earthquake that causes more damage, or a large storm that carries more sand away from a waterfront. But how much energy? Let's put some numbers on this. You will recall that waves are propagating vibrations, and we've already looked quite a lot at the energy of such vibrations. This is concerning the energy of the simple harmonic oscillators. We know that the total energy of such an oscillator equals a component of its kinetic energy, a half mv squared, plus its potential energy, a half kx squared. And we also know that when the speed equals the maximum, our potential energy is zero. This is what happens when, say, the mass on the spring is in between the two positions. Here we have the maximum speed and zero potential energy. This is useful because we can knock out one section of our equation now, and we can write here that E potential equals zero when Vmax equals, and you might remember we calculated this as omega A, where omega equals the angular frequency and A equals the amplitude of the vibration. Now we can write that our total energy equals a half m omega squared A squared. Now we want to get rid of the mass, so this isn't specific to one particular type of vibration, and we can do that by remembering that density equals mass per unit volume. So this big V here, this is volume. Therefore mass equals density times volume, and if we replace mass with density times volume, and we can see that our energy now equals this relationship here. We can rewrite this as energy density by dividing both sides by a volume. So now we have energy per unit volume, which is the energy density, equals a half rho omega squared A squared. So the amount of energy per unit volume, the energy density, carried by a wave is proportional to the square of the amplitude A. E on V is proportional, remember this little sign here is a proportionality sign, A squared. That means when the amplitude gets big, the energy density really gets big. So now let's talk about sound intensity. Intensity is the energy transported by a wave per unit time through a plane of unit area perpendicular to the direction of the wave's movement. We can write this down as power per unit area. So intensity equals power over area. For a sound wave, we can just use velocity and the relation we got on the previous overhead and show that intensity equals a half V, and this V here is wave speed, density, A squared omega squared, where V equals the wave speed, rho equals the density of the medium, A equals the amplitude, omega equals the angular frequency, and A, sorry, is the amplitude of the wave, and it's the angular frequency of the wave. Intensity has the units of power per unit area, so it's watts per meter squared, or joules per second per meter squared. Let's talk a little bit about point sources and spherical waves. For a point source, spherical waves radiating outwards from that point source will be seen. I can try to draw it here. So we have a point source in the middle. The waves generated from this point source will be radiating outwards. If you think about a child standing in a swimming pool and jumping up and down, these are the waves that are generated by that disturbance. So the intensity of the waves at a position away from the point source can be written as the power of the source divided by 4 pi r squared, where this is the power from the source and r squared is the distance from the source. Now this is because the surface area of a sphere equals 4 pi r squared. So this is really just an expression of energy conservation, because obviously as the wave spreads out, the area it covers gets larger, so therefore the intensity has to decrease. This is what's called an inverse square law. Intensity is proportional, and this is this proportionality sign again, to 1 on r squared, where r equals the distance from the source. Now, it's useful to know the following. If we know the intensity and the distance, we can take the ratios of these relationships and work out the intensity without needing to know the power at the source. I'll show you what I mean. So if we say we have intensity 1 equals PS, the power at the source, divided by 4 pi R1 squared, and somewhere else we've measured intensity 2, and it equals the power at the source divided by 4 pi R2 squared. Now we can take the ratios of these two things, so intensity 1 divided by intensity 2, and we take the ratio of the other side, so PS 4 pi R1 squared divided by PS 4 pi R2 squared, and if we're dividing by this element here, we can just turn it around, multiply it out, and we can see it a bit more clearly. Now we can cancel out the power at the source and our 4 pi's, and we're just left with the ratio of the radius. So we have R2 squared on R1 squared. Let's write this out over here. So the intensity ratio I1 on I2 equals the ratio of R2 squared over R1 squared.